Sean todos bem-vindos no podcast de hoje. And if you are wondering why we just started off with a little bit of Portuguese there, it's because we are taking a trip down to Brazil today.
We are indeed.
Yeah, but before we get to the laboratory at Unijui, which is where this all happens, I want you to imagine a scenario. So you're driving home late at night, and you see those flashing red and blue lights in your rearview mirror.
All the worst feeling.
Right. The absolute worst. You get pulled over, the officer walks up to your window and asks for your driving license.
Standard procedure.
Exactly. Normally, you just pull out your wallet, you hand over a little piece of plastic, but I want you to really think about what is actually printed on that piece of plastic.
Right. It's not just that you can drive.
No, not at all. It has your full legal name, sure, but it also has, like, your exact home address, your date of birth, your height, your weight, your eye color, whether or not you are an organ donor.
It's a massive data dump.
Yes. You hand all of that over to a stranger just to prove one single piece of information, which is just, yes, I have the legal right to operate a motor vehicle.
Right. It's wildly inefficient from a privacy standpoint.
Exactly. So imagine an alternative. The officer asks for your license, and instead of handing over the plastic card, you pull out your phone.
Correct.
The officer scans a QR code on your screen, and your phone mathematically proves to the officer's device that you hold a valid state-issued license.
But it doesn't give them anything else.
Right. It reveals absolutely nothing else. No address, no age, no weight, just a green check mark indicating, yes, this person can legally drive.
Which is how it always should have been, honestly.
Seriously. So today, we are looking at the actual deployed technology that makes that possible right now. We are doing a deep dive into a really cutting-edge research paper titled Unlocking the Potential of Decentralized Digital Identification Systems for Smart Cities.
Yeah, it's a fantastic paper.
It really is. It's authored by Carla Castaño and a whole team of researchers spanning Brazil, the University of Cambridge, and the Alan Turing Institute.
Some serious heavy hitters in there.
Definitely. And our mission today, really, is to understand how we can reclaim our digital identities from the ground up, using this tech.
And it is an incredibly timely piece of research.
Yeah.
I mean, we completely take identity for granted in the physical world, right?
Right.
We have our passports, we have birth certificates, social security cards. But in the digital world, the underlying infrastructure of identity is, well, it's actually quite fragile.
Fragile's a good word for it.
Yeah, we've basically built this massive, globally interconnected society on top of a digital identity system that is, in many fundamental ways, completely broken.
Yeah. And the paper starts by defining what a digital ID actually is at its core, which seems like a basic question until you really try to answer it.
Right, it gets complicated fast.
It does. Because who actually proves you are who you say you are online? If I show you my physical passport, you trust it because the government issued it and they have authority.
Exactly.
But when I log into, say, a hospital portal or an online bank or a municipal service, who is acting as the authority there?
Well, the researchers use this term, and it's super important. They call it the root of trust.
The root of trust. Okay.
Yeah, the root of trust is basically the cornerstone of this entire architectural discussion.
Yeah.
To define a digital ID, we have to look at it as a specific data structure,
Right.
like a unique string of characters.
Okay, string of characters.
Right, and that string is firmly associated or bound to a unique entity.
And an entity, just to clarify, that doesn't just have to be a human being.
No, not at all. Especially in the context of a smart city. I mean, an entity could be a smartphone, it could be an autonomous bus, a smart traffic light, or even like a software service managing the local water grid.
Oh, wow. Okay, so everything gets an identity.
Exactly. But for our purposes today, let's just look at it from the perspective of a citizen. So, attached to this unique string are attributes.
The data points.
Right. These are the characteristics defining the citizen in a specific context. So, name, biometrics, residency status, things like that.
Right, so the citizen presents this ID to a service to make a claim, like, I am this person, let me access my municipal tax records.
Yes. But the city portal can't just take that claim at face value.
Because I could just be lying.
Exactly. So the service requires authentication. The citizen has to cryptographically prove ownership of that unique string.
Makes sense.
And equally important, honestly, is the concept of revocation.
Oh, right. Like if I lose my phone.
Yes. If that citizen's phone is stolen, that digital ID must cease to be valid instantaneously across the entire network.
So nobody else can pretend to be me.
Exactly. Authentication and revocation are the two load-bearing pillars of any identity system. But this brings us back to your question about the root of trust. Like,
Mm.
who holds the ultimate authority to issue and revoke?
Right. And currently, on the internet, we rely almost entirely on a centralized approach, don't we?
We do, and it's highly problematic.
Yeah, this is where things get really uncomfortable because we rely on the Web Public Key Infrastructure, or Web PKI,
Right.
and that's controlled by just a tiny handful of massive certification authorities like DigiCert or VeriSign, or, even more visibly to the average user, we just rely on the tech giants.
Oh, completely.
Like, how many times a day do you click a button that just says log in with Google or log in with Apple?
Way too many.
Well,
And in those systems, that corporate entity operates as the ultimate root of trust. They literally hold the keys to the kingdom.
yeah.
If Google decides to suspend your account, for whatever reason, your digital identity effectively ceases to exist across thousands of third-party platforms.
Which is terrifying.
It is. And the Unijui researchers draw a very hard line here. They argue that if you are trying to build a true smart city, a deeply interconnected urban environment where traffic grids, hospital records, public transport, all of it is talking to each other digitally.
Right.
If you do that, outsourcing your city's root of trust to a private centralized corporation is a massive vulnerability.
Because it creates a catastrophic single point of failure.
Exactly.
But the paper goes even further than just the security risk, which is interesting. They outline this structural critique of these centralized monopolies. Like, first, there's a total lack of openness.
Right. A city shouldn't need permission from a tech giant just to operate.
Exactly. Or have to pay exorbitant licensing fees to a corporation just to let its own citizens access public services.
Yeah, that makes no sense. And there's also a severe lack of transparency. You as a citizen have absolutely zero insight into how your authentication data is being managed or stored or correlated within their black box servers.
You just have to blindly trust them.
Right. Which leads directly to the third and probably most urgent threat here, abusive data monetization.
Oh, yeah. The data harvesting.
Yeah. When a central authority controls the root of trust, they inherently have visibility into the data flow. They know when you log into the hospital. They know when you log into the transit app, when you access your bank.
They see everything.
And that metadata is incredibly valuable. The incentive to exploit it for profit is immense.
It essentially means the foundation of our digital lives is built on rented land, and the landlord is reading all of our mail.
That is a perfect way to put it.
So the alternative is decentralized digital identities, a system where no single corporation or government server sits in the middle.
Right.
And this is the big question. If centralized systems are so obviously flawed, and we've been talking about blockchain and decentralization for, over a decade now?
At least.
Why hasn't it happened? Why isn't this already the global standard for every city on Earth?
Well, because building a system that requires absolutely no central authority yet remains perfectly secure, scalable, and crucially legally compliant is honestly one of the most difficult engineering and legal puzzles of our generation.
Legal compliant being the key word there.
Huge keyword. The friction isn't just technical, it is fundamentally legal. The researchers point specifically to the stringent requirements of modern data protection laws.
Right, like Brazil's LGPD, the General Data Protection Act.
Exactly, and the European Union's GDPR.
Yeah, this clash between privacy laws and decentralized technology is so fascinating to me. Because these laws were drafted with the best of intentions, right?
Absolutely.
They were designed to protect citizens from exactly the kind of corporate data harvesting we just talked about.
Right.
And one of the fundamental pillars of the GDPR is the right to be forgotten. If you request that a company deletes your personal data, they are legally obligated to scrub it from their servers entirely.
Which is a great law in theory.
Yeah.
But that legal mandate runs headfirst into the foundational architecture of a blockchain.
Because you can't delete things on a blockchain.
By its very definition, a blockchain is an append-only, immutable digital ledger.
Right.
Once data is written to a block, and that block is verified and added to the chain, it is mathematically linked to every block that came before it and every block that comes after it.
It's locked in forever.
Permanently. It's etched into the network, replicated across thousands of independent computers globally.
So you have an irreconcilable paradox here.
You really do.
You have a law that says you must be able to delete this data on demand, and you have a technology designed explicitly so that data can never, ever be deleted.
Exactly.
You can't just serve a subpoena to a blockchain. You can't call up the CEO of Ethereum and ask them to, delete block number 5 million. It just doesn't work that way.
It really doesn't.
Yeah.
And if a city were to put a citizen's home address or even an encrypted version of their medical records directly onto a public blockchain, it would be a catastrophic violation of the GDPR from day one.
Even if it's encrypted.
Even if it's encrypted. Because encryption standards weaken over time. What takes a supercomputer 100 years to crack today might take a quantum computer 10 seconds to crack a decade from now.
Oh, wow. I didn't even think about that.
Yeah, so if that encrypted data is sitting permanently on a public ledger, it is a ticking time bomb.
So how do you thread that needle? Because the UniJui team is still advocating for a blockchain-based solution in this paper. How do you use an unerasable ledger without violating the right to be forgotten?
The architecture demands a very strict separation of concerns. You have to ensure that absolutely zero sensitive personal data is ever stored on the blockchain itself.
Like nothing at all.
Nothing, not even in an encrypted format. The actual data remains entirely off-chain. It's typically stored locally on the user's own smartphone in a secure enclave.
Okay, so then what is the blockchain actually doing?
The blockchain is used exclusively as a verification registry. Think of it as a public bulletin board for cryptographic proofs rather than a database for the actual information.
Okay, and the paper brings up zero-knowledge proofs, or ZKPs, as the mechanism that makes this possible.
Yes, ZKPs are essential here.
We should really break down how a zero-knowledge proof works, because honestly, it sounds like magic the first time you hear it.
It really does.
How do you mathematically prove that you know a piece of information without revealing the actual information itself?
It is a profound cryptographic breakthrough.
Oh.
But let's step away from the math for a second and just look at it conceptually.
Okay, I love a good analogy.
Right. Imagine you and I are standing in a room, and on the table between us is a massively complex, intricately detailed Where's Waldo poster.
Okay, standard Where's Waldo. Thousands of characters on the page.
Exactly. And I make a claim to you. I know exactly where Waldo is,
Okay.
but I refuse to point him out to you because I don't want you to know his location.
Naturally, I wouldn't just take your word for it. I'd demand some kind of proof.
Right. So to prove my claim, without revealing the underlying data, which is Waldo's coordinates on the page, I take a massive, completely opaque piece of cardboard, much larger than the poster itself.
Okay.
I cut a tiny, tiny hole in the cardboard, just big enough to show Waldo's face. I place the cardboard over the poster, and I shift it around secretly until Waldo's face perfectly aligns with the hole.
Got it.
Then I invite you to look. You look through the hole, and you see Waldo.
I see him, so I know for an absolute fact that you found him. You have proven your claim.
Right.
But because that giant piece of cardboard completely obscures the rest of the poster, I have zero context clues.
Exactly.
Like, I don't know if he's in the top left corner, the bottom right, next to the striped tent, or the hot air balloon. I have zero knowledge of his actual location, but 100% certainty that your claim is true.
That is the absolute essence of a zero-knowledge proof. And translated back into the digital realm of smart cities, it means you can prove to a municipal service that your income qualifies you for a specific public transit subsidy, for example.
Without ever revealing your actual salary.
Exactly. Or you can prove you are a resident of a specific voting district without revealing your home address.
That is so cool.
Right. The blockchain simply holds the cryptographic equivalent of that cardboard cutout, the mathematical proof of the claim.
And that beautifully sidesteps the GDPR problem.
It really does.
Because if I decide I want to exercise my right to be forgotten, I just delete the underlying data off my own smartphone.
Yep.
And the cryptographic proof that remains permanently etched on the blockchain is entirely useless without my local data. It's just a mathematical hole in a piece of cardboard with nothing behind it.
Exactly. It reveals nothing, so privacy is maintained perfectly.
Wow. But arriving at this elegant off-chain architecture didn't just happen overnight, did it?
Oh no, it took years of trial and error within the developer community.
Yeah, the researchers actually conduct an autopsy of 3 pioneering decentralized identity systems in the paper, just to illustrate why earlier attempts couldn't quite serve as the ultimate foundation for a smart city.
It's a really valuable part of the paper.
Let's look at those pioneers, because their failures are incredibly instructive. The first one they evaluate is ePort, which was built on the Ethereum network.
Right. Now, ePort was a brilliant early experiment in user autonomy. It was really one of the first real attempts to let users control their own digital identities via smart contracts.
But it ran into issues.
It did. Because it was built directly on Ethereum in its earlier, less mature iterations, it struggled fundamentally with the immutability conflict we just discussed.
The privacy law clash.
Yeah. In those early days, the architecture often required writing more identity state data to the chain than was strictly necessary.
Which is a big no-no.
Right. It made it very difficult to align with strict privacy regulations without employing highly complex, expensive, and gas-heavy workarounds.
Gas meaning the transaction fees on Ethereum.
Yes, exactly.
So Uport had the right ethos, but the raw Ethereum environment of the time just made legal compliance too cumbersome. Okay, so the second system they looked at was Sovereign. And now, on paper, Sovereign looks like exactly what a smart city would want, right?
It really does.
It's designed explicitly for global identity applications, and it inherently uses a protocol called AnonCreds, which is specifically built to handle those zero-knowledge proofs for privacy. I mean, it seems perfect.
Technically speaking, Sovereign is a remarkably robust and well-designed system. The researchers totally acknowledge its technical merits. But Sovereign has a fatal flaw, and it's not a flaw in its cryptography. It's a flaw in its macroeconomics.
Macroeconomics. Okay, explain that.
Well, Sovereign is a dedicated blockchain. It operates its own independent, bespoke network built entirely for the single purpose of identity management.
Which means it requires its own global network of computers to run it.
Precisely. And running a globally distributed decentralized ledger requires hundreds or thousands of independent nodes.
Servers, essentially.
Servers running around the clock. They are consuming vast amounts of electricity. They require physical maintenance, cooling, massive bandwidth. It is an expensive physical operation.
Right, servers aren't free.
No, they aren't.
Yeah.
In a system like Bitcoin, for example, the operators of those nodes, the miners, are rewarded with newly minted Bitcoin.
So there's a financial incentive to keep the servers running.
Exactly. The network pays for its own physical security through a highly liquid, highly valuable financial incentive.
And Sovereign doesn't have that.
Sovereign operates on a different consensus model. It relies essentially on trusted institutions, they call them stewards, to operate the nodes.
Okay.
But they often do this without a massive speculative financial reward attached to the computation itself. It relies heavily on the goodwill, the shared interest, or just the nominal operational budgets of the consortium members.
Oh, I see the problem. Goodwill doesn't pay the server hosting bills.
It definitely doesn't. Without a clear, overwhelming economic incentive to motivate these disparate global participants to continuously spend real-world money maintaining the ledger, the network's long-term survival is precarious.
Yeah, if the budget dries up, the nodes shut down.
Exactly. If the institutions running the servers face a budget cut, or they simply lose interest in the project, nodes go offline. And if enough nodes go offline, the network dies.
Wow.
The Unihui researchers are actually remarkably blunt in their assessment here.
What do they say?
They speculate that without a radical shift in its underlying economic model to incentivize node operators, the Sovereign network is likely to shut down in the near future.
That is blunt. And you cannot build a multi-decade smart city infrastructure like tying your hospitals, your traffic grids, and your voting systems to a ledger if you suspect the ledger might just evaporate in 3 years because the server admins ran out of funding.
It's an unacceptable risk for a municipality.
Right. So that brings us to the third system they evaluated, Hyperledger Indy.
Now this one is different.
Yeah, because it allows for the creation of bespoke private networks. You aren't relying on a public group of volunteers. You can build your own walled garden.
Which is very appealing to municipal governments who inherently want control.
Of course they do. But the barrier to entry here is extreme implementation complexity and political friction, right?
Huge friction. Hyperledger Indy isn't just a simple software package you download and execute. It is an enterprise-grade framework.
Okay.
To deploy it, a city can't act alone. They have to assemble a massive, coordinated consortium of trustworthy legal entities.
So the city government has to get, like, the local universities, the major banks, the regional hospitals, and maybe the utility companies into a room, and they all have to agree to participate.
Yes. And before a single line of code is written, you are looking at months, if not years, of legal wrangling.
Just the meetings alone.
Oh, endless meetings. You have to draft memorandums of understanding. You have to agree on a governance structure like who has the right to read, who has the right to write to the ledger.
What a headache.
And then every single one of those institutions has to allocate significant financial resources. They have to procure servers, hire specialized blockchain IT staff, and manage their own nodes. It is an incredibly heavy lift.
It's like a city deciding they want to issue a new type of bus pass. But to do it, they first have to form an international treaty organization, build a new telecommunications grid, and establish a parallel legal system.
That's a great analogy.
The bureaucracy and the capital expenditure alone make it a complete non-starter for most mid-sized cities.
Which leads the researchers to a highly pragmatic conclusion.
What's that?
If building a bespoke network like Indy is too politically complex and expensive,
Yeah,
and relying on an underfunded, dedicated network like Sovereign is too risky,
right.
then the ideal solution would be to find a way to piggyback on an indestructible network that already exists.
A network that someone else is already highly incentivized to maintain.
Precisely.
And this is where we get to the core architecture proposed in the paper, utilizing a system called Trustchain.
Yes, Trustchain is the key here.
But before we get into the specifics of how Trustchain performs this exact trick, we really need to make sure we truly understand the vocabulary and the moving parts of a decentralized identity ecosystem.
It's crucial. Yeah.
Because we are completely shifting the paradigm away from the usernames and passwords we are used to.
Totally different mental model.
The researchers provided this beautifully detailed conceptual map in the paper. Let's walk through the architecture of this map because it fundamentally rewires how trust works on the internet.
It does. It actually takes us back to the way trust works in the physical world, but enforces it with cryptography instead of physical security guards or watermarked paper.
Let's start with the central figure in the map, the entity.
Okay, so as we established earlier, this is the citizen, let's call her Alice, or a specific IoT device.
And Alice's primary tool in this ecosystem is something called a verifiable credential.
Right. Think of a verifiable credential as the digital evolution of a physical document.
Like a university diploma, a driving license, a union membership card.
Exactly. It is a standardized, machine-readable package of claims about Alice.
Okay.
Alice holds these credentials securely in a digital wallet on her own device. When she wants to interact with the smart city, say, applying for a residential parking permit, she presents the relevant credential to a service.
But I can't just, open a text document on my phone, type, I have a PhD in astrophysics, and expect the university to give me a teaching job.
Sadly, no.
Where do these verifiable credentials actually come from? The conceptual map points to two distinct upstream providers, the certification provider and the authentication provider. Why are there two?
Separating these roles is actually crucial for a scalable, flexible system. The certification provider is the ultimate authority that generates and issues the credential.
So in the physical world, this is the Department of Motor Vehicles or the University Registrar's Office.
Exactly. They are the legal entity authorized to state, yes, Alice passed her exams. They cryptographically sign the credential and issue it to her wallet.
Okay, so they are the issuer. Then what does the authentication provider do?
The authentication provider manages the ongoing life cycle and valid state of that credential.
Ongoing life cycle.
Yeah, they are the entity trusted to verify, at any given moment, if the credential is still valid or if it has been revoked.
Ah, right. The revocation we talked about earlier.
Yes. Often, an organization will act as both like the DMV issues the license and also maintains the database of suspended licenses.
But they don't have to be the same.
Exactly. Separating the roles allows for delegation. A university might be the certification provider for a diploma, but they might outsource the actual cryptographic authentication uptime to a dedicated municipal IT service.
That makes total sense. So Alice has her verifiable credential from the certification provider. She takes it to the municipal portal to get a parking permit. The portal, in this scenario, is acting as the verifier.
Correct. The verifier is the entity validating the credential upon presentation.
So if Alice is trying to enter a secure municipal building, the electronic turnstile is the verifier.
Yep. And the verifier's job is to look at the credential Alice presents and ask 3 questions.
What are they?
Was this actually signed by the legitimate certification provider? Has it been altered in any way since it was signed? And has it been revoked?
In the physical world, a bouncer at a club answers those questions by, shining a little black light on an ID card to look for a hologram and maybe bending the plastic to see if it feels right.
Right, very analog.
But in this digital architecture, the verifier relies entirely on DD's decentralized identifiers. These seem to be the fundamental building blocks of the whole map.
The EDs are the atomic unit of decentralized identity, absolutely.
What exactly is a DDD?
A DD is simply a unique identifier, a long string of alphanumeric characters formatted in a very specific way.
Okay.
But unlike a standard URL that points to a specific server owned by a corporation, a DD resolves to a DD document.
The map explicitly breaks down the relationship around the DD into two roles, the D subject and the DD controller. I want to explore this distinction because it clarifies a lot about how machines and humans interact in this space.
It's a very important distinction. The DDI subject is the entity being identified by the D-Day.
So Alice is the DY subject of her personal D-Day. A specific city bus is the D subject of its operational D.
Right. The DD controller, however, is the entity that possesses the actual cryptographic private keys required to modify the corresponding DD document.
So in a purely self-sovereign system, Alice is both the subject and the controller. She controls the keys to her own identity.
Exactly. But consider the city bus. The bus is the subject, but the bus doesn't have agency. It doesn't have fingers to type a password.
Right.
The DD controller for that bus would be the city's Department of Public Transit. They hold the keys that can update the bus's service records or revoke its operational status on the network.
Okay, so the verifier looks at Alice's D-ID and it resolves to her D-Day document.
Yeah.
What is actually inside that document? Because we established earlier that we absolutely cannot put her personal data on a public ledger due to GDPR.
Right, no personal data. The D-ID document is essentially a decentralized public key certificate, typically formatted as a simple JSON file.
Okay, so just code.
Just code. It contains absolutely zero personal attributes. Instead, it contains the cryptographic public keys associated with the DD subject.
Just the keys.
Just the keys. And it also contains service endpoints.
What are those?
They're essentially URLs, where a verifier can engage in secure, encrypted communication with the entity.
So let me trace this path. The verifier looks at the verifiable credential Alice presented, which was signed by the DMV.
Yep.
The verifier looks up the DMV's DID document, finds the DMV's public key, and does the cryptographic math to ensure the signature on Alice's credential perfectly matches.
Exactly.
If the math checks out, the credential is mathematically proven to be authentic and unaltered.
That is exactly how it works. No humans needed in the loop for the verification.
Which leaves only one final piece of the architectural map, the verifiable data registry.
The verifiable data registry is the public bulletin board. It is the system that securely stores all of these DID documents and makes them globally accessible. When the verifier needs to look up the DMV's public key, they look it up on the verifiable data registry.
And here we arrive back at the massive hurdle that Sovereign and Hyperledger Indy failed to clear for the Unijui team.
The infrastructure problem.
Right. What serves as this verifiable data registry? Who hosts the bulletin board? If you build your own blockchain, it's too expensive, too politically complex, and requires constant economic life support.
Yeah, it's a nightmare.
You need a registry that is already funded, already globally distributed, and functionally indestructible.
Which brings us to the core thesis of the paper and the genius of the Trustchain protocol.
Yes.
Trustchain solves the registry problem through sheer pragmatism. Trustchain itself is not a new blockchain.
That's a crucial point.
It's just free open source software. Its explicit goal is to create a public key infrastructure without ever needing to rely on trusted intermediaries to manage or maintain the servers.
The researchers outlined 5 core pillars of Trustchain that give it a massive advantage over previous iterations. Let's run through them. First is open access.
Right, meaning anyone, whether it's a citizen in Santa Rosa or a software developer in Tokyo, can deploy a Trustchain node and participate in the network without asking for permission or prior authorization from any tech company or government body.
Beautiful. Second is low cost.
Because the software is open source, and, crucially, it does not require the creation or maintenance of a new, bespoke blockchain.
No server farms to build.
Exactly. The operational costs and complexity are slashed to near zero.
Third is transparency.
Verifiers can fully audit the cryptographic signatures and see the legal entities involved in each issuance process, making the entire chain of trust completely visible.
Fourth is privacy.
Adhering strictly to the off-chain architecture we discussed. All personal credentials are stored locally on the user's device, ensuring absolute compliance with data protection laws and giving the user total sovereign control over their information.
And finally, the fifth pillar, high security. And this is where the Trustchain protocol pulls off its greatest trick, doesn't it?
Oh, it really does.
It achieves unparalleled security by anchoring its verifiable data registry entirely to the Bitcoin network.
Yes. Trustchain relies on the existing, globally distributed Bitcoin peer-to-peer network.
When I was reading this section, an analogy jumped out at me.
Let's hear it.
Trustchain operates exactly like a hermit crab.
A hermit crab, okay.
Yeah. Think about it. A hermit crab is a vulnerable creature. It needs a hard, protective shell to survive. But growing a heavy, calcified shell takes an immense amount of biological energy and resources.
Right.
The hermit crab doesn't have that energy, so instead, it wanders along the ocean floor, finds the most massive, indestructible shell that some other creature has already spent the energy to create and subsequently abandoned, and it just takes up residence inside it.
I love that.
Trustchain does the exact same thing. It doesn't spend billions of dollars and megawatts of electricity building a new blockchain to secure its data. It simply takes shelter inside the most indestructible digital shell humanity has ever engineered: Bitcoin.
That is a remarkably apt way to visualize it. And we really need to drill down into what makes that shell so indestructible.
Yeah, let's talk about the math and the physics of it.
We need to talk about thermodynamics and proof of work, or POW, because the security of Trustchain, and therefore the security of this entire smart city identity model, is entirely reliant on the massive computational mining power of the Bitcoin network.
The paper drops a staggering statistic about the hashing power of Bitcoin.
It is a number that is almost difficult to comprehend. The researchers note that the Bitcoin network generates approximately 800 exahashes per second.
Let's put that in perspective for a second. A hash is essentially a computer making a mathematical guess to solve a highly complex cryptographic puzzle.
Yes?
800 exahashes means the global network of Bitcoin miners is making 800 quintillion guesses every single second.
It's mind-boggling.
That is an 8, followed by 20 zeros, every second of every day.
It is the largest single deployment of computational power in human history, drawing gigawatts of raw electrical energy.
And why does this matter for Alice trying to get her digital parking permit?
Because at this scale of thermodynamic energy, altering the Bitcoin blockchain retroactively is economically and physically infeasible.
Because to rewrite the history of the ledger, say, a hacker wanting to change the DID document of the city's transit authority, they would have to outcompute the rest of the entire global network.
Precisely. They would need to amass more than 50% of that 800 exahash power.
Which is impossible.
Even if the largest tech corporations or a coalition of nation-states pooled all of their supercomputers together, they couldn't overpower the network to rewrite a block that was published yesterday.
The power draw alone would be insane.
Right. The thermodynamic cost of an attack is so astronomically high that it is effectively impossible. This is the absolute physics-based immutability that secures Trustchain's data registry.
But this brings up a massive debate in the crypto space. The researchers explicitly note that they rejected other consensus mechanisms.
They did.
They didn't use networks based on proof of stake or POS or proof of authority or POA. A lot of modern blockchains use proof of stake precisely because it doesn't consume all that electricity. Why would the UniJui team actively choose the energy-intensive proof-of-work model?
This cuts to the very philosophical core of what trust actually is in a digital system.
How so?
In a proof of stake or proof of authority system, the security of the network is maintained by specific entities, validators, who have staked massive amounts of financial capital or who have been granted explicit authority by a governing body.
Okay.
Therefore, to trust the integrity of the network, you inherently have to trust the infrastructure operators. You have to trust that the cabal of wealthy validators won't collude to alter the ledger.
But the entire mission of a decentralized identity system is to eliminate the need to trust middlemen.
Exactly. Systems like POS or POA rely on digital signatures that inherently require a pre-existing public key for validation.
Yeah.
It becomes a recursive chicken-egg problem of trust. Who watches the watchers?
Right.
Proof of work is fundamentally different because it is objective, not subjective. It is tied to raw, verifiable thermodynamic energy.
The physics.
Yes. It allows any user, anywhere in the world, to independently verify the public keys and the exact publication dates of data without trusting anyone. You don't trust a validator's reputation, you trust the laws of physics and mathematics.
So Trustchain essentially sneaks its DID documents, or rather the cryptographic hashes that prove the existence of those documents, into standard Bitcoin transactions.
Yep.
It anchors the trust of the smart city to a network secured by raw physics while keeping all of the heavy private data securely off-chain.
It is a brilliantly elegant architecture. It's supremely secure, it aligns with privacy laws, and crucially, it requires zero infrastructure investment from the city deploying it. They just pay tiny transaction fees to the Bitcoin miners.
Okay, so the theory is bulletproof. The hermit crab strategy makes total sense. The architecture map is sound.
It is.
But theory is easy in an academic paper. Does it actually work when you try to build it?
the moment of truth.
This is where the paper becomes incredibly valuable because it transitions from theoretical computer science to a practical step-by-step roadmap. The researchers didn't just theorize, they set up a virtual machine right there in their lab at UniJui and deployed the entire system from scratch.
Yes, and they documented the entire process. They essentially wrote the recipe for how a municipality can actually bootstrap a smart city identity network today.
Let's look at the ingredients they used. It's a fascinating tech stack. They spun up a Linux Debian 12 virtual machine.
Standard, reliable.
They utilized Rust for the backend cryptography. They used Node.js for the server environment. They used MongoDB for the database. And they relied heavily on a critical piece of middleware called ION, the Identity Overlay Network.
Let's expand on why they chose these specific tools, because it highlights the reality of modern software engineering.
Why Rust, for example?
They used Rust because it is a memory-safe language. In cryptography, memory leaks or buffer overflows can lead to catastrophic security vulnerabilities where private keys are exposed.
And Rust prevents that.
Rust prevents those at the compiler level. It's incredibly secure.
And Node.js.
They use Node.js because it is highly efficient at handling thousands of asynchronous HTTP requests, exactly what you need when a city full of smartphones is constantly pinging a server to verify credentials.
Makes sense. And what about MongoDB and ION? Where do they fit into the architecture?
ION is the vital bridge. Remember, Trustchain wants to anchor its data to Bitcoin, but Bitcoin is slow and expensive.
Right. It only does a few transactions a second.
Exactly. It can only process a few transactions per second. If a city generates 10,000 new DDIs in a day, writing each one directly to Bitcoin would cost a fortune and take hours.
Which is not feasible for a city.
Not at all. ION solves this by batching. It takes thousands of DD operations, compresses them into a mathematically verifiable cryptographic tree, a Merkle tree, and writes only the tiny root hash of that tree into a single Bitcoin transaction.
It's like putting thousands of letters into one single shipping container and just logging the container's tracking number on the blockchain.
Precisely. And the actual DD documents, the letters in the container, are stored on the Interplanetary File System, or IPFS, which is a decentralized peer-to-peer storage network.
And MongoDB.
MongoDB is used locally by the Trustchain node simply to index all this data so that when a verification request comes in, the server can look it up instantly without having to parse the entire Bitcoin blockchain every time.
But wait, if ION is the middleware doing the batching and writing to Bitcoin and IPFS,
Yeah.
don't we inherently have to trust the developers of the ION software? Doesn't that reintroduce a middleman?
This is the beauty of cryptographic verification. Absolutely no trust is placed in the ION software itself.
How is that possible?
Because after ION performs its batching and writing, the Trustchain node independently downloads the data from IPFS, retrieves the hash from the Bitcoin blockchain, and recalculates the entire cryptographic tree itself.
It double-checks the math.
It does more than double-check. If ION tries to lie, if it drops a DID or alters a key, the mathematical proof simply won't add up, and Trustchain will reject the entire batch instantly. The math polices the middleware.
That is brilliant. Okay, so the team is in the lab. They have their virtual machine, their Rust, their Node.js, and ION. They break down their deployment into 7 distinct phases. Let's walk through these because this is how a city's digital infrastructure is actually birthed. Phase 1 is funding the wallet.
Right. While storing the data on IPFS is largely free, embedding that cryptographic hash into a Bitcoin transaction requires paying a minor fee. The network requires a toll.
So did the researchers have to ask the university accounting department for a budget to buy real Bitcoin on the open market?
Fortunately, no. For development and testing, they utilize the Bitcoin testnet. This is an exact parallel replica of the main Bitcoin network. It has the same rules, the same cryptography, but its native token, TBTC, is freely distributed from developer faucets and holds absolutely zero real-world financial value.
Oh, that's convenient.
So they generated a wallet and collected enough fake TBTC to fund their experimental transactions.
Okay, phase 1 is done. The wallet is funded. Phase 2, publishing the root DID. This is the genesis moment of the entire trust network.
This is where the municipal authority establishes its digital existence. A legally authorized entity, let's say the mayor's office acting as the root authority of the smart city, generates a master cryptographic key pair and publishes its root DD to the blockchain.
But this presents a massive logical problem.
Look up.
If I'm a citizen living in this city and I see a random string of alphanumeric characters pop up on my Trustchain app claiming to be the mayor's office,
Yeah.
how do I know it's actually them? How do I know it's not a hacker sitting in a basement who just generated their own DID and labeled it City Hall? Where does the very first drop of trust come from?
You have identified the most critical vulnerability in any decentralized system, the initial leap of trust. How do you bridge the gap between the physical world and the digital cryptography?
Right.
The researchers leveraged the one thing the Bitcoin network provides perfectly: objective time.
Objective time. Okay, how does that work?
When the mayor's office publishes its root D-Day, that transaction is permanently time-stamped by the mining network. Let's say that block was mined on October 15th, 2025 at exactly 10:00 a.m.
Okay.
The city authority then takes that specific date and time and initiates a massive physical world public relations campaign.
You mean they advertise it?
Exactly. They broadcast that specific date on local TV news broadcasts. They print it in full-page ads in the local newspapers. They splash it across highway billboards.
Wow.
They print it on official municipal tax bills sent to every home. The official digital identity of our city was established on October 15th, 2025.
Oh, I see.
As a citizen, you only need to know that one single, highly publicized fact. Because when you enter that date into your app, the app scans the blockchain and verifies that the DID created at that exact moment is mathematically linked to all subsequent official city services.
You bridge the physical world's consensus everyone saw the billboard with the digital world's immutable math.
Exactly.
It is so simple, yet so incredibly effective. You anchor the cryptography in shared physical reality. Okay, so the root D is established. Phase 3 is creating downstream DIDs, or DDIDs.
Once the root D exists, it acts as the anchor point for the entire city's organizational chart. The root authority can now cryptographically sign the DIDs of other legitimate legal entities, creating a verifiable tree of trust.
So the mayor's office uses its private key to sign a downstream DID for the Department of Transportation, another for the public hospital network, and another for the city university.
Right.
How does that exchange actually happen securely? The mayor doesn't just email a cryptographic key to the hospital, right?
No, definitely not. It is handled via an automated challenge response protocol.
Challenge response.
Yes. The hospital runs its own independent Trustchain node. The hospital generates its own key pair and sends a request to the mayor's node. Please sign my public key.
Oh.
The mayor's node responds with a challenge, a cryptographic puzzle that includes a nonce, which is a random number used only once, encrypted with the hospital's public key.
So only the hospital can solve it.
Exactly. The only way to solve this puzzle is if the hospital actually possesses the matching private key. The hospital's node decrypts the nonce and sends it back. This proves possession of the keys without ever exposing them.
Ah, clever.
Once the mayor's node verifies the correct response, it signs the hospital's DID document. Now, any citizen scanning the network knows the hospital is legitimate because the mathematically verified mayor vouched for it.
So we are building out the hierarchy of the city, branch by branch. Phase 4 is setting up the HTTP server. This is where the system actually connects to the real internet so citizens can use it. They had to set up issuance and verification endpoints via an HTTP API.
This step transitions from abstract cryptography to standard IT infrastructure, but it's where things must be locked down tightly.
Right.
The Trustchain server needs a fully qualified domain name, or FQDN. It cannot simply broadcast an IP address. It needs a verifiable web address that the mobile applications can reliably locate.
And crucially, it requires robust transport layer security, or TLS.
Exactly.
The researchers note they had to get their university network administrators to explicitly open port 443.
Yes. Port 443 is the global standard for secure encrypted web traffic, HTTPS.
Which we use every day.
Right. To ensure that the communication between a citizen's phone and the city's server cannot be intercepted or manipulated by a man-in-the-middle attack, the team used an automated service called CertBot to generate a Let's Encrypt certificate.
This guarantees that when a user requests a credential, the data pipe itself is absolutely private. Which brings us directly to Phase 5, the mobile app. This is where the theory hits the pavement. This is the listener's perspective. For the end user, all of this Rust code, MongoDB indexing, and Bitcoin hashing is completely invisible.
Exactly as it should be. The citizen simply opens the Google Play Store or Apple App Store and installs the Trustchain mobile application.
What happens the moment they launch the app for the first time?
The application utilizes the secure, cryptographic enclave built into modern smartphone hardware to locally generate a brand new, unique personal deed ID for the user.
From a freshly minted, a public-private key pair.
Yes. Crucially, that private key never, ever leaves the physical device. It is not backed up to a corporate cloud.
So Google doesn't have it. Apple doesn't have it.
Nobody has it but you. Then the app asks the user for one single piece of onboarding information, that root DD calendar date they saw on the billboard.
So I type in October 15th, 2025.
Yes, and the millisecond you hit enter, the app goes to work.
What's it doing?
It reaches out to the network, scans the blockchain for the DID published on that exact date, verifies the root, and then automatically traces all the cryptographic signatures down through the branches to the DOT, the hospital, the university.
Oh, wow.
It instantly maps out the legitimate service endpoints for the entire smart city. Your phone now mathematically knows exactly who to trust.
Okay, let's put the system to the test. Phase 6, issuing a digital driving license.
This is the fun part.
The researchers simulated an ISO 12013 standard credential, which is the actual international standard being developed for mobile driving licenses.
Yes, very realistic test.
In this test scenario, the entity playing the role of the Department of Transportation, which has a mathematically verified downstream DID, needs to issue a license to our user, Alice.
Right.
The DOT's HTTP server generates a QR code on their web portal. Alice pulls out her phone, opens the Trustchain app, and scans the QR code on her computer screen.
But notice what happens before any data is transferred.
What?
The app reads the QR code, which contains a URL pointing to the DOT's server endpoint. The app immediately checks its internal trust map.
The one it built from the billboard date.
Exactly. It verifies that this specific URL precisely matches the legitimate DoD document that traces all the way back to the root authority.
So it completely neuters phishing attacks.
Absolutely.
If the hacker built a perfectly cloned fake DOT website and generated a QR code, Alice's app would scan it, realize the URL doesn't mathematically trace back to the October 15th billboard date, and instantly block the interaction.
Precisely. The math prevents the fraud.
That's amazing.
Once the app silently confirms the endpoint is legitimate, it alerts Alice. The verified Department of Transportation wants to issue your driving license. Do you accept?
She taps yes.
She taps yes. The cryptographic exchange happens, and the verifiable credential is securely stored directly in the local wallet on her phone.
Which sets up the grand finale of the experiment, Phase 7, device-to-device verification. Let's go back to the scenario we opened the deep dive with.
The traffic stop.
Right. Alice is driving. She gets pulled over by a police officer. How does she prove she can drive without handing over her home address, her weight, and her date of birth?
This is where those zero-knowledge proofs we discussed earlier come alive in a real-world interaction.
Okay, walk me through it.
The police officer has their own municipal device, also equipped with the Trustchain application, and synced to the city's trust network.
Walk me through the actual interaction at the car window.
Alice opens her app and selects her driving license credential. But instead of displaying the full digital card, she invokes a feature known as a verifiable presentation.
Okay.
She is given granular control. She actively toggles which specific attributes she wishes to disclose.
So she checks boxes.
Yes. In this scenario, she selects only her photograph so the officer can visually confirm it's her, and a simple Boolean value, a true-false statement confirming valid license, true.
So she actively redacts everything else, the address, the age, all of it.
Yes. And the app performs cryptographic magic based on Merkle trees. It generates a new, temporary cryptographic proof that effectively says, I am Alice, here is my photo. I hold a valid license issued by the verified DOT. And even though I am hiding 90% of the data on this credential from you, the underlying digital signature from the DOT remains mathematically unbroken and valid.
Wow. And the app packages this complex mathematical proof into a simple QR code on Alice's screen.
Yeah. The officer scans Alice's QR code with their device. The officer's app instantly recalculates the math, verifies the DOT signature against the blockchain registry, confirms the credential hasn't been added to a revocation list, and flashes a green screen.
Instant verification.
The officer knows with absolute cryptographic certainty that Alice is licensed to drive. Alice's privacy is flawlessly preserved. And here's the most important part.
Yeah.
This entire transaction at the side of the road happened device to device. It required absolutely no central server to mediate the interaction. The city didn't log that Alice was pulled over at 11:30 p.m. on Main Street.
That is an incredibly triumphant proof of concept. But whenever you read an academic paper detailing a flawless tech demo, you have to ask, what was the actual human cost of building it?
Right. The real-world friction.
Because this brings us to the final section. Was it easy?
The researchers are refreshingly transparent about the pain points of this deployment.
Yeah, they document that it took 2 researchers, an undergraduate and a PhD student, approximately 60 hours of active work to get this system fully operational in the lab.
60 hours.
60 hours. For 2 people who actively study computer science and blockchain architecture, I mean, if you've ever spent 3 hours just trying to get a new wireless printer to talk to your home router,
It's the worst.
imagine trying to configure a decentralized identity node from scratch. Why on earth did it take them a week and a half of full-time work?
Well, it wasn't because the fundamental architecture was flawed. It was the inherent friction of navigating bleeding-edge open-source technology.
They were pioneers hacking through the jungle.
Exactly. They hit significant hurdles due to documentation gaps in the public repositories. The instructions simply weren't perfectly complete.
That happens so often with open source.
It does. Furthermore, they ran into maddening technical glitches born from default configuration errors. They faced strict university firewall rules blocking necessary peer-to-peer connections.
Ah, the port 443 issue.
Yeah, and they dealt with database indexing mismatches between ION-N and MongoDB.
It sounds like a nightmare.
At one point, the friction was so high they actually had to solicit remote, real-time guidance from one of Trustchain's core developers located in the UK just to troubleshoot some of the thornier dependency issues.
That is the brutal reality of GitHub repositories. But there is a massive silver lining to their struggle, isn't there? Because they didn't just high-five and publish the paper when they finally got it working.
No, and this embodies the true spirit of open-source scientific collaboration. After they successfully deployed the node, they went back and fixed the Git documentation.
They updated the manual.
They updated the public manuals, filling in the gaps and clarifying the configuration steps based on everything they had painfully learned.
That's awesome.
They estimate that with their newly refined, paved roadmap, a municipality attempting a reinstallation from scratch today would only need about 20 hours of work and wouldn't require any remote hand-holding from developers in the UK.
They cut the deployment time by 66% just by leaving a better map for the next team.
Exactly.
And let's put that 60 hours or even 20 hours into macroeconomic perspective. The researchers make a very strong point about this. Yes, 60 hours of debugging is frustrating, but doing this via existing open source tech and the Bitcoin network saved tens of thousands of hours and millions of dollars compared to a city trying to code, launch, and secure a brand new decentralized ledger from scratch.
Absolutely. The return on investment is astronomical. They proved conclusively that Trustchain is not just a theoretical concept. It is practical, deployable infrastructure that rests firmly on the shoulders of massive, already existing open-source networks.
So they proved it works in a lab. What is next on the horizon? Because the UniJUI team isn't just stopping with a virtual machine.
No, the immediate next steps are highly practical. They are moving directly into rigorous scalability testing.
What does that entail?
Well, it is one thing to issue a driver's license to a hypothetical Alice. It is another entirely to ask, can this specific node architecture handle 50,000 DIDs pinging the server simultaneously during a morning commute?
Right.
What happens to the verification speed on a standard 5-year-old Android phone when a chain of downstream DIDs gets very long and complex? They need to stress test the math.
And they're going to answer those questions by rolling this out to real human beings.
Yes.
The paper outlines their concrete upcoming projects. They are actively creating a smart campus at UniJUI.
A live testbed.
Yeah, they're going to issue live, verifiable DDs to real university students and staff, allowing them to use their phones to access physical campus buildings, log into university Wi-Fi, and access library services.
And even more ambitiously, they are formalizing partnerships with the local municipal government.
Out in the real world.
Right. They are planning to expand this exact infrastructure beyond the university walls and out to the citizens of Santa Rosa City, allowing residents to access municipal tax portals, health services, and transit systems securely and privately using the exact architecture we've detailed today.
When you take a step back and look at the totality of this research, it really reframes how we think about our daily interactions.
It does.
Think about your physical wallet again. It is stuffed with vulnerable plastic health insurance cards, gym memberships, library cards, university IDs.
It's all just sitting there waiting to be lost.
And think about your digital life, likely managed by a password manager holding 300 different logins, half of them tethered to a Google, Apple, or Microsoft account.
The central points of failure.
Right. This research from Castaño and the Unijui team isn't just an abstract academic exercise in cryptography. It is the architectural blueprint for how all of those physical cards and all of those vulnerable, centralized passwords could be entirely replaced within the next decade.
Replaced by a single, cryptographically secure enclave on your phone.
Yeah, that gives you, and only you, total granular control over exactly who gets to see your data and when. It is the technological end of the invisible middleman tracking your every move.
That is a very powerful synthesis of the journey we've taken through this paper.
It's been a journey.
We started by confronting the fundamental security flaws, the lack of transparency, and the profound privacy risks of our current monopoly-controlled identity system.
Well, we navigated the incredibly complex legal paradox, where data protection laws like the GDPR directly collide with the immutability of blockchain ledgers.
We saw how early decentralized systems like Uport, Sovereign, and Indy stumbled over that immutability, or failed to solve the macroeconomic problem of incentivizing network nodes, or simply collapsed under the weight of enterprise bureaucracy.
And we arrived at Trustchain's remarkably ingenious solution, the digital hermit crab.
Bypassing the need to build a new network by anchoring a local, off-chain, privacy-first credential system directly into the staggering thermodynamically unhackable computing power of the global Bitcoin network.
It is a profound structural shift in how the digital world can operate.
It is a complete inversion of power.
It really is.
And I want to leave you, the listener, with a final thought to ponder something that builds on everything we've explored today, but pushes into philosophical territory that even this technical research paper only begins to hint at.
Okay, let's hear it.
Think deeply about what it means to truly, fundamentally own your identity.
Own your identity.
For centuries, across the entire span of human civilization, our identities have always been granted to us by an intermediary. A king, a church, a state government, and now massive transnational tech monopolies.
Right, they hold the keys.
Legally and practically, we exist because they issue a piece of paper or a database entry saying we exist.
Yeah.
They hold the root of trust.
Yeah.
But if a decentralized public key, anchored in objective mathematical certainty and thermodynamic physics rather than institutional authority, is all you need to definitively prove your existence, your rights, and your qualifications.
Does the fundamental relationship between the citizen and the state begin to alter?
Exactly. Once your identity is entirely in your own hands, stripped of the invisible middleman and secured by math, what else becomes possible for the future society?
Wow. That is a massive paradigm-shifting question to chew on. Because if you control the root of trust, you ultimately control your own digital destiny. Thank you for joining us on this incredibly deep dive into the future of identity. Keep exploring the technology, keep questioning the systems around you, and remember, just because there is an invisible bouncer at the door today doesn't mean we aren't already inventing a better way to get inside tomorrow.